Good afternoon, everyone. Thank you very much for joining this panel on machine learning, deep learning, AI for EDA. My name is Prit Banerjee. I'm the CTO for ANSYS. I joined the company about 8 months ago. My background is I used to work in the EDA industry for many, many years when I was in academia for about 20 years. And more recently, I've worked in companies like HP Labs, the CTO at ABB and Schneider Electric. It is an absolute pleasure to be back at DAC talking about the future of electronic design automation. Today, the topic of our conversation is on emerging design and implementation and sign-off challenges for sub-7 nanometer, 5 nanometer, 3 nanometer designs, both design and implementation for SoC designs. And the question that we'll ask is, with all these newer verticals that are coming to us, autonomous vehicles, AI, high-performance computing, mobility, 5G, with all these newer areas that we are working on, will AI, ML allow us some new ways, new approaches to solve really, really difficult problems? As many of you know, right, with sub-7 nanometer designs, we have tremendous challenges with we're trying to do ultra low power, challenges with reliability, challenges with thermal, challenges with mechanical, all kinds of things that are simultaneously coming to us. So the question is, could we, when we are dealing with dynamic voltage drops at ultra low voltage, how do you do these kind of designs, right? And so the challenge, these are becoming very, very challenging. And so can AI ML help us in those things from an accuracy point of view, from a runtime point of view, and from an ease of use point of view? So to address this particular exciting topic, and a lot of very interesting technical talks at DAC, at this year's conference, I'm joined here with a very distinguished panel. On my immediate left is Brusek Kailani from NVIDIA Corporation, and he's going to, as you know, many of you know, NVIDIA is absolute leader in AI ML with some of their DGX1 platforms and so on. So he's going to bring some perspectives on AI ML in this area. Next to him is Burak Kara from Carnegie Mellon University. He's done a lot of exciting research in this topic, and again, you will hear from him. Next to him is Ali Khairala from Ericsson Corporate Research. He's going to talk about some of the things around 5G and some of the challenges there. Next to him is Dwayne Boning from MIT. He's a professor at MIT in ECS. And finally, we have Sorin Dobre from Qualcomm Technologies. So we have a very, very distinguished panel. What I'm going to do is to ask each of the panelists to introduce themselves, their organization, some of the things that they're working on, and then we'll go into the actual topic of the panel. So let's start with you, Brusek. Let's talk about your background.
Okay. Hi, my name is Brusek Kailani. I manage the ASIC and VLSI research group at NVIDIA. So it's part of the overall NVIDIA research organization, which is about 150 people spread all over the world, mostly in the US and Europe. And we do fundamental research and applied research into all aspects of NVIDIA's technical business. My group specifically focuses on next generation design methodology, as well as accelerator design techniques. A lot of our focus has been on improving design productivity, but most recently we've kicked off an effort within the last year or two on applying deep learning and GPU acceleration to EDA problems with the focus of publishing papers to basically explain these techniques, and in some cases working with universities to release open source software and so forth. Thanks.
Thank you. Burak?
Good afternoon. My name is Burak Kara. I'm a professor of mechanical engineering at Carnegie Mellon University with a courtesy appointment in the Robotics Institute. My research is in the field of computer-aided design, and my research is at the intersection of mechanical engineering, industrial product design, and computer science. And within the computer science field, mostly computer graphics and machine learning. So what we do in our lab is develop new design methods, design theories for shape design, structural design in the context of mechanical engineering. So we're developing a lot of data-driven methods that can be the future ingredients of the mechanical CAD design tools. And most recently, some of the things that we have done, we saw that we could actually extrapolate that to the space of EDA, and we're now working on a project that involves machine learning-driven, data-driven global routing in the space of EDA. Even though I have no background in that, it has been fascinating to see that some of the background actually translates into these new domains.
Thank you, Burak. Ali?
Hi, I'm Ali Kairala from Ericsson in Santa Clara. So I manage a team that's part of the Ericsson Corporate Research Organization. And we're in the so-called radio area, which means that we work on designing air interfaces for 5G and beyond 5G and so on. So currently we're working on topics like NR, which is the acronym for New Radio in 5G, NR for unlicensed bands, NR for high frequency, some satellite applications, and so on. Previously, we worked on topics like narrowband IoT and LTE-M, which is another IoT mode of LTE. So my specialty is more on the signal processing and communication systems and information theory side. So not quite what I presume most of this crowd is, but I hope we can provide an interesting, different perspective.
Thank you, Ali. Dwayne?
I'm Dwayne Bonning, professor in electrical engineering and computer science at MIT. There I'm also the faculty co-director for the MIT Leaders for Global Operations program, which is a dual MBA and Master of Science, dual program between the Sloan School of Management and the School of Engineering. And what's interesting there is it focuses on the manufacturing and operations industries where we're seeing a lot of interest in the uptake of machine learning and AI technologies. My own research is in the interface between manufacturing and design, mostly semiconductor. So I've been interested in design for manufacturability, DFM, using whatever tools I could get my hands on or help develop, whether it be physical modeling, empirical modeling, statistical learning, and now machine learning.
Thank you, Dwayne. Finally, Soren?
Hi, my name is Sorin Dobre, and I'm part of the design technology team in Qualcomm. My team is focused on advanced technology. We are enabling the implementation for all the system on chips, which are actually manufactured by Qualcomm. The focus for my team is in advanced technology, design for low power, timing methodology, design for yield, design for manufacturability, IP optimization, and PDN optimization. Now, in terms of machine learning, we are actually very active in developing and optimizing design flows, EDA flows. We are working very closely also with the EDA companies to develop new tools and then to develop, let's say, flows which can address the design needs for these SoCs implemented in 7 nanometer, 5 nanometer, 4 nanometer, 3 nanometer process technology.
Thank you, Soren. So I hope you agree that we have got an outstanding panel. They clearly are leading wonderful research groups, either in academia or in the corporate world. And if anybody can, they can answer this question. So I'm going to ask each of the panelists to make their position statement on the key idea of the panel. There's a lot of hype around AI, machine learning, deep learning, right? And you have all heard this sort of Gartner hype curve, right? So the question that we face today is, not if it's interesting, is AI/ML applied to EDA, is it a hype or is it a reality? And they don't all have to agree. In fact, I hope that a few of the panelists will disagree about the thing that is. Some of them will say it is hype, some will say reality. But we are going to go around and ask each of the panelists to make a short statement about whether AI/ML applied to EDA is a myth or reality in the face of these sort of challenges that we said, autonomous vehicle design, AI chips, HPC, and so on and so forth, and the fact that the sort of the voltages are going down, the sizes are going down from sort of 7 nanometer to 5 to 3 and so on, and we have all these thermal reliability, all these challenges. So with that, let me start with you, Brusek, about your position. What do you think on this topic?
Thanks. So I definitely believe that AI or ML for EDA is going to be reality very soon. I think we can start with the fact that EDA, Electronic Design Automation, or the Design Automation Conference, it's all about automation. And our CEO likes to say that AI is essentially the automation of automation. Rather than creating software that does the automation yourself, you create very simple software programs, feed patterns into these machine learning models, and you basically get automation directly from the data. So, so my position is, although it probably hasn't quite arrived yet, we've had enough early indicators of key success and some research studies to show that it is quickly going to become a reality. And the kind of I'll give three kind of areas where we think that there's a strong potential here. So one is problems where there's no easy analytical solution to something. So there's been a few papers that have published about how do you predict the probability of encountering a DRC after just doing placement, basically as you go downstream through the tools. You can't really solve that directly, but it turns out that you can do much better than traditional heuristics by just looking at past data and like inferring some, and creating a model that basically can give you a prediction based on all the features that you get from doing placement. So that's one example. Another example where we see a lot of benefit is by doing approximate solutions to simulations that otherwise would take orders of magnitude more time to simulate exhaustively. So a good example here, we just actually had a paper from one of our former interns presented about an hour or two ago, where he showed that rather than running gate level simulation and power analysis on the activity factors extracted from a gate level simulation, you can infer the propagation of activity factors through a netlist by using a trained model, and then just feed in the results of your RTL power simulation and get about 1 to 2 orders of magnitude faster than it would have taken to do the same analysis using gate level power analysis. And then the third area that I think it will be a reality is sort of augmenting existing tool flows. So pretty much every EDA tool has heuristics like sprinkled throughout the code everywhere. And this is exactly what machine learning is really good at. Rather than creating hand-coded heuristics, we can just essentially train a model to provide heuristic estimates back to the tool. And so a lot of these places where heuristics are used, I think will likely get replaced with machine learning inference in the loop.
Thank you. Thank you very much. Burak?
Well, if we ask the question...
Feel free to be controversial, right?
Sure.
We want an interesting panel here.
Well, in my judgment, I think it is already a reality in the following sense. So if you look at any AI ML as a whole package and then open it up into its different segments, different techniques, our classical optimization, that is part of the ML, and ML heavily relies on that. And there are tools both in the EDA space and mechanical engineering space that make use of optimization, for decades now. I think what we mean by ML in this context is that we imply the notion that can we learn from past designs? Can we learn from good and bad designs in order to inform future designs? And I think this is what we imply by saying ML for EDA. I think we're not there yet. But the biggest opportunity that I see is, agreeing with you, is for creating fast simulators for physics that are very difficult to simulate in real time. I think ML has a huge potential there. We are actually dabbling in a similar problem in the mechanical engineering domain, which is called stress analysis. Basically, it's a sophisticated PDA that you have to solve. It can be very expensive if you're going to embed this into a topology optimization routine, for instance. There are a lot of parallels to this in the EDA space. So if you can accelerate that inner loop, which is a simulation loop, even if it's not 100% accurate, you can actually gain so much through the power of ML. And I think that is happening. We definitely in the academic circles that's happening. It's accepted to be a reality. Perhaps the general population has not seen the impact of that yet, but we're in that wave currently that in the next 5-10 years, it is going to be a reality. It is going to be expected.
Very good, thank you. Ali?
Okay, so I have somewhat of a bad news, good news story. So in my area, there's a basic issue of where you have structure and where you don't have structure. So at the so-called lower layer, physical layer, we spend a lot of time using all kinds of theory and algebra and geometry and whatnot to make things nice and symmetric and beautiful and whatnot so that the receivers can be effective. So that kind of structure is not suitable for ML in my opinion. And there's probably not a big gap that you could fill by, doing ML-like techniques which are less structured. And in addition, we have a very rich theory behind what we do, like information theory and communication theory and all these things. And in many cases, we know how close we are to the limits. So I think in that narrow sense, I don't believe this is where ML would be effective. However, if you go to higher layers, like in a mobile network, we do a lot of resource allocation, which user is allocated to which frequency and time and so on. And there you have all kinds of problems which are very unstructured and also not even fully understood, right? So even though we do have nice solutions because you already have mobile networks, whether it's 5G or not 5G, but we're not really sure that, is this the best thing? Is there other things and so on? So there you can see that you have these enormous high-dimensional problems with very little structure. And I would think that techniques like ML would really do very well there. So it's kind of a bifurcated story, and it's yet to be decided.
Very good. Dwayne?
On the question of myth or reality, I would say both. Right? Certainly the realities are already machine learning, particularly those related to reduced order modeling, regression, classification, and so on are in use, working their way into the tools. The myth part, I think, is twofold. First is the idea that somehow deep learning is going to displace all of the other approaches of machine learning. So my first sort of message is machine learning is a much broader notion than convolutional neural network deep learning pipelines. And the second myth is that that's the tool for every problem. As we heard, I think that we're already seeing applications of other rich areas of machine learning that grow out of and augment statistical learning, design exploration, and so on, that are actually even more interesting and applicable potentially, with a lot of hard work, to EDA, in part because the structure that feeds deep learning isn't quite the structure we have. We are not in a big data world. We're actually in a very small data world. The cost of each labeled piece of data that we need to feed into supervised learning is much higher than getting a label, is that a picture of a cat? So, I think we've got lots of opportunities. It's already working its way in, but I think we're in a very interesting sort of subdomain where we're a little different than the big singular move towards deep learning. There are some problems where mapping onto that pipeline will be tremendously useful also in our domain. But that's where I think a lot of interesting work and opportunities will arise.
Thank you, Dwayne. Soren?
From Qualcomm, I think we have kind of multiple points of view. So first of all, we're trying actually to use machine learning to optimize our internal flows and tools. So we see a significant opportunity to improve our hardware utilization, software utilization, license usage. So we have a significant development for the internal design flows actually to implement. So these are the solutions which are developed actually in-house, which are using machine learning. From the EDA point of view, we believe that all these machine learning algorithms, they will move from the periphery of EDA to the center of the EDA tool. They will become actually embedded at the core technology for all the EDA tools. There is a significant opportunity, especially for the tools which are generating a lot of data, actually to have visibility and then to create these models on the fly. So you don't have to generate the data and then later to actually start to create the model. So as you generate the data, you can actually create different type of models. Now, when these let's say machine learning algorithms will move to become a core technology for these all these EDA tools, we believe that the interaction between the designer and the EDA tools actually is going to change. You're going to have much better QOR, much faster type to quality results coming from, let's say, this new generation of EDA solution. Now, beyond that, there's going to be a next generation of, let's say, acceleration in machine learning when we're going to have hardware embedded, let's say, subsystems in the computing space, which actually is going to accelerate by 2 orders of magnitude all these, let's say, generation of the models. So today, in all the SoCs which are going in the cell phones, there is actually a subsystem for machine learning, for artificial intelligence. I don't see why for the general computing we're not going to have these hardware accelerators, which are actually extremely efficient and have the capability to accelerate the generation of these models by 2 orders or 3 orders of magnitude. So that is going to be the next wave, maybe the third wave of implementation of machine learning actually in hardware and the direct benefit in the design and EDA space.
Thank you, Soren. So I think you all shared some very, very interesting insights. I mean, at ANSYS, which is, again, a sort of simulation company that has tools across fluids, structures, electromagnetics, semiconductor, and so on, we have also seen some key ways that AI/ML can have an impact. And the first, and I think they were sort of summarized there. So I just wanted to compile what we have just heard and from my personal insights from ANSYS. The first thing is many of these EDA tools, I mean, can be semiconductor tools or it could be mechanical tools or whatever, right? These are really, really complicated things you're trying to solve. You're solving second-order partial differential equations using finite element method, this type of meshing, that type of stuff. So it oftentimes requires a very sophisticated user to set the parameters in these tools, use finite element, finite difference, this solver, this thing, tetrahedral meshing, and so on. And you almost need a PhD to run the tools, right? And once you know how to do these things, then it runs really sort of blazing fast. So as an output of a simulation, what you need to do is go for really better accuracy and faster runtime. And so how you tune these parameters are in the heads of this PhD level designer. Those things can be learned by AI/ML. So that's one general category, and we are seeing a lot of benefits in that area. The second one, I think Burak mentioned this, right? So simulation typically takes a long time because you're trying to solve these with partial differential equations, Maxwell's equations, Navier-Stokes, and so on. And the question is, can you train a deep neural network model to say you apply input X, get output Y, you apply input X2, get output Y2. And just by training for a whole set of different inputs, can you train a neural network to replace simulation? As he's talked about, it's like a faster simulation. This is like the holy grail. A lot of people are working on this. There are some challenges about how we can do it or not, but I think that's the sort of second category. And the third category, this is what sort of Burak works on in the whole area of generative design. Why do people do CAD and so on, simulation, right? Because as a designer, you're trying to try this one, that one, 3 or 4 different combinations. Well, with generative design, you can automatically test for 10,000 different cases, and the best 3 will be proposed to you. So those are 3 broad areas, and I see all 3 areas as having tremendous impact to this area. So just wanted to hear from what you all talked about and some of our own learnings within ANSYS. Now I'm going to go and sort of ask pointed questions to individuals, and in the past 2 times I went through sequentially, so you knew exactly who I'm going to ask questions to. Now I'm going to be totally randomized. We'll start with you, Ali. So you are at Ericsson, right? And again, a lot of people are talking about 5G as this is going to solve all our problems, right? I mean, 10 gigabits per second speed, less than 1 millisecond of latency, and because of these things, you're instead of having these base stations every couple of miles, you now have it at every crossroad. So how does 5G differ from 4G and 3G and all that kind of stuff, right? In terms of the EDA process, if you can talk about, and in that sort of applied, talk about the role of AI/ML. So how is 5G different from 4G and 3G in terms of the EDA sort of solutions, and how can AI/ML impact that, if you can talk about it?
So I think there was a session a couple of hours ago that addressed 5G and everything that doesn't work in it and so on. That made me feel very sad, but it works, trust me. But what 5G is bringing for an infrastructure manufacturer is that the base station is being broken up into pieces. So not only do you take things to centralized computation baseband, which has been going on, but also because of the high bandwidth and the high bit rates and the very large number of antennas, especially at high frequency, you are pushing more and more of the electronics towards the antenna, right? And this is kind of a completely different architecture than what we used to have before, where the base station was essentially like an extremely large phone. Everything was together, right? But now, just out of necessity, and because we can do more things with antenna arrays, we are pushing electronics, not only radio electronics, but also baseband electronics up to the antenna. And that is creating like a whole new world for us. And of course, we have already solved it once because we are deploying 5G with all the US operators and many others. However, I think there's a completely open area for design, for 5G and for beyond 5G, where people can rethink of how they design these things, what processing happens near the antenna, and so on. And maybe this is another area where more unstructured techniques, as I think of them, like machine learning, could come in and completely blow the thing apart.
Thank you, Ali. So we are going to go to the other company that is betting on 5G, Qualcomm. So Soren, I'm going to ask you, what do you think are sort of the unique challenges in this area? Sort of similar to the question I asked Ali, right? And how can AI/ML help in the sort of solutions, the whole EDA tool flow?
So just to give you a little bit of perspective, so from Qualcomm point of view, we are actually at the 3rd or 4th generation of 5G modems. So first 5G modem actually we have implemented commercially in 10 nanometers. 2nd generation, it's in 7 nanometer. 3rd generation, it's in 5 nanometer. And then we are working on the 4 nanometer and 3 nanometer implementation. Now the 10 nanometer, it's actually in the phones. You can actually buy the phone. To answer your question, what is the difference between a 4G and a 5G modem? Because of the computations requirement for 5G, we are trying to get to this 3 to 5 to 10 gigabits per second. These 5G modems actually are large, and then also they consume a lot of power. The biggest challenge we are seeing right now for the 5G deployment at the SoC level, it's actually power density. So these 5G modems, actually, if you look to the power consumption, peak current area, they are actually very close to a GPU. Now, if you go from 10 nanometers to 7 nanometer to 4 nanometer, you're going to get the area scaling. The area scaling, actually, you get a very good area scaling. You're going to get performance improvement. You're going to get some power reduction. But the power reduction doesn't follow exactly the same scaling with the area scaling. So you do have actually an increase in power density. So power density is actually the #1 challenge for 5G SoC. So thermal solution, designed for low power, designed for low voltage. Actually, that's the main focus, to build a viable, very low power, and actually commercially effective 5G SoC, which actually integrates everything. It's not only the modem, you have the CPU subsystem, GPU subsystem. As I mentioned, you have this neural network subsystem. So there is a lot of actually functionality in these SoCs, and we cannot have the 5G modem actually being 30% of the die, or consuming the same power, having the same power profile as a GPU. So now how the ML or AI actually can help us, it's actually to help us accelerate the development process in actually adopting these new technologies. So when you go from, let's say, 7 nanometer, 5 nanometers, we start actually very, very early, when these processes actually, they are not very mature. So design for yield, to build models, actually we have a better, let's say, yield prediction. Then in terms of building all the PDKs, to build all the libraries, I think ML solutions, are actually provide the significant values, because you can get all the IPs and all the collaterals very early. And also building models for physical design implementation, for thermal design, for system level thermal designs. We see a significant benefit actually coming from this, let's say, development in the area of ML. That is the reason we see this technology actually migrating to the core technology of these tools for thermal analysis, physical design, standard cell characterization or IP characterization, PNR, timing sign-off, airdrop sign-off. So all these tools actually can use these models, and then can increase the efficiency of overall PPA for physical design implementation, and the final actually footprint in terms of power consumption, in terms of energy, and then in terms of cost for these 5G modems.
Thank you, Soren. So I'm going to change sort of topics a little bit. I know the panel is on EDA, but this whole area of AI/ML has been applied in the mechanical area to great sort of excitement. And I want Burak to talk about his experiences in this area of topological optimization, generative design. We had a great lunch discussion on the topic. So can you tell us about what has worked in your sort of mechanical CAD field? And maybe in the EDA industry, we can get some inspiration in a sort of interdisciplinary manner. So talk about generative design.
Sure. And I get very excited talking about generative design in the mechanical engineering context. I'll try to keep it short, but I want to seed an idea potentially. When we talk about generative design, it actually promises something magical, in my opinion. It means that a human designer is no longer designing the geometry, but we are accustomed to thinking that human designers' jobs are to design the geometry, right? So when we think about design, we think about somebody sitting in front of a computer drawing on a CAD program. The ultimate goal of design is not that. It is to achieve an objective function. So if we can actually think about design in this light, I think we can cast any design problem, EDA, mechanical, as a pure optimization. ML can go into helping that optimization. But a human designer's job should not be about predicting or specifying the geometry. It should be about thinking about the constraints, thinking about the function, and human designers are not necessarily good at this. So what I'm very excited about is seeing how ML technologies can actually move the human designer from thinking about the, prescribing the geometry to this high-level functional thinking. In our research, what we have seen is that for conventional classical problems like topology optimization under static forces, the moment that you make that problem slightly more difficult by saying, if my forces are moving across the surface, what should the design look like? A human engineer won't be able to tell you that. And using ML, we have shown proof of concept results where you can actually get very interesting solutions, topology optimization solutions, or in the EDA space, that would be like a layout optimization. You get very interesting solutions. So generative design is currently giving a lot of powers to the designer. I just want to make one final remark about this. One thing that is very important in any design context is the idea of past designs. Can you learn from good and bad past designs, right? And ML, I think, is very, very useful in being able to learn these distance functions across the existing designs. If you can actually lay out a very high dimensional distance field that will actually tell you all the pairwise distances, you can do so much with that information. And we are seeing quite a bit of work in the mechanical engineering domain targeting only that aspect of machine learning with so far seemingly good results.
Wow, that is very inspirational. So we are going to go into the audience participation point now. So if you can we'll set up a microphone in the front, and if you can line up here to ask questions. As you prepare to start thinking of the questions, I have a couple of more questions to ask, but please, we are looking for audience participation here. So please line up here, and otherwise I'll keep asking questions to the panelists here. So please come to the microphone. So Brusek, your company CEO has literally bet the future of NVIDIA on AI/ML. I mean, you are doing all the gaming engines, video cards, and so on. Now it's all about AI/ML, right? So what are you thinking, right? Really look into the future. Where is it headed?
Yeah. So I guess I'll talk about, so most of AI and what's been deployed like in production today is generally supervised learning. So feed lots of examples to a model and have all the examples be labeled by, usually by humans. You have some large labeled data set or by some other tool. And then you recognize those patterns and then basically do an inference where you play back the basically the same where you're able to basically do that pattern recognition later in production. But where AI is moving is from supervised learning to either a weakly supervised thing where you use some sort of a lot more data and you feed heuristics and you assume there's noise in your data set that you're labeling, or along the lines of what Barak was talking about, where you have something kind of more unsupervised where you're doing generative models or like a reinforcement learning. So, if you listen to what the experts in AI say, that's just going to mean larger models, more data, and so forth. I think that similar trend will also apply in the EDA space. So far, most of the examples have been using supervised learning, but I think maybe the real breakthroughs may come as we apply these other techniques.
Fantastic. So thank you, sir. You are coming in. So please ask your question, but introduce yourself and then ask your question.
Very good. So Mike McNamara from Adapt IP. A bunch of years back in the back end of EDA, we introduced open access to allow you to plug in tools and bring other techniques and basically do time analysis and so on. Do we need an architecture that lets us bring in ML and AI techniques into the traditional tool flow, or is this going to be something that the CAD vendor implements themselves and we just get the results? Do you see a call for some kind of OpenML access into EDA tools?
Soren, you opined on the topic of ML in the area of tool flow, so why don't you get the first?
Actually, I hope it's working. So we are seeing both developments. So we are developing even internally solutions for ML which are augmenting the existing, let's say, EDA solutions. And also we are working with the EDA vendors to accelerate the development for ML. So for timing specifically, there is a significant opportunity. That's what we are seeing from our, let's say, design experience in, let's say, increasing the throughput, reducing the running time, and actually taking advantage of the massive data we generate for, let's say, this complex SoC. So we see a kind of very sweet combination between ML and cloud computing, where you can actually scale and parallelize the jobs. And to answer your question specifically, I think there is a great opportunity for the EDA industry actually to accelerate this development and then for this solution to become native parts or solutions. But also there is a great opportunity for new startups because they can move actually much, much faster without any baggage and then take advantage of the massive data which is generated by any design house and actually provide these ML solutions which can actually accelerate and help the design flow significantly. So both solutions actually are viable solutions.
And I'd just join in.
Yeah.
and say I think that there's tremendous need and tremendous opportunity for much more open access to both the design data, but also the design experience data. Generative design or reinforcement learning, et cetera, those tools are going to, or those methods, need much richer access to the full experience, the full sets of state and state transitions that designers and the tools have gone through to explore that space and do that much more efficiently in the future. There are some efforts, sort of nascent, or I would say pleas, calls for action, maybe not efforts yet, to try to achieve a little bit more openness of across suppliers and across tools, both to enable the access of the machine learning into the tools, but also access of that data to enable the very development of those kinds of sort of higher order machine learning techniques.
Thank you, Dwayne. Let's move on to the next question. Thank you. And again, if other people want to come in, please join. We have about 5 more minutes.
Yes, thank you. Thalum Kiley at Mythic in Austin, Texas. So initially I was kind of skeptical about the notion of heuristic components of the software being replaced by machine learning techniques. But then I thought, well, given the fact that you need a lot of data to generate your inferences from, could the heuristics be somewhat turned around to supply the data? Is there either ongoing efforts in that specific point, I wonder?
Maybe we'll have these 3 people respond first. Can you repeat the question, please?
So was the question, so there's somebody somewhere in the middle brought up the problem of the size of the data, right? And so I'm thinking in terms of acquiring data to supply to the learning, could the heuristic algorithms that are used be somehow turned around to become data providers? You see what I'm saying?
Yeah. So just to jump in real quickly, I think any sources of prior knowledge are incredibly valuable. Some of that prior knowledge may be physical models and the physical simulation to help prime the pump of a machine learning model. Heuristics would be another great example, but I think they're wonderful as maybe even a starting point for further exploration and discovery of new, subtler heuristics that a human brain wasn't able to come up with. But you get to that point to start it, because it's really hard for a machine learning algorithm to roam around and rediscover some of these heuristics. But if you are able to sort of pre-train it, it's quite a powerful launching off point.
Something to say now? Okay.
Well, I'll just add one thing. Yeah, so I mean, I think what you're hinting at is what a lot of people talk about as weakly supervised learning, where you basically apply some heuristics to your data set and realize it becomes a noisy label, essentially. And so that's one of the active areas in AI that people are exploring.
So I wanted to ask a provocative social question at the end. When you see different industries that are getting disrupted by AI and ML, right? Look at all these truck drivers, those 2 million truck drivers that will lose their job once those truck things are automated. So it is now 2019. Do you think by the year 2050 that AI/ML will be so advanced in the area of EDA that we will not a single designer, DAC will be completely empty, so half empty this year, it will be completely empty, that you will not need designers. So the question, and literally yes, no kind of a thing, right? Do you think by 2050, in about 30 years, AI/ML in the EDA industry will be so advanced you will not need designers? Let's start with you, Burak.
Yeah, this is a tough question, predicting the future. I will say that historically speaking, that has happened in many, many industries. Anytime a new technology develops, it's a moving front, right? So it sweeps out the existing human jobs, it replaces them. But if you look at the last few hundred years, the overall quality of life of the average human has increased dramatically. Yes, there will be people impacted by this automation. And there's a big question, who benefits from this automation? It usually is the corporations, it may not trickle down, so I think that's a bigger philosophical debate. But if you're asking, are jobs gonna be lost? I would say yes. Is this an absorbable, can we digest this issue? I think the answer is yes also. We no longer have people switching boards when we make a phone call, like that has been automated. We don't have what is called city criers, where they break the news to the big cities. We don't have those jobs anymore. So I think if you follow a similar pattern, yes, jobs will be lost, but a human for engineering will always be necessary. So I think we're going to be somewhere in between.
One other panelist, I asked for their input.
Yeah, I mean, I think it's how you use it. If you think of it as a tool in the toolbox of whatever area you're in, you say, oh, this is a neat tool, we can use it to advance whatever we're doing. Then I think it fits within a relatively smooth advance of your area. I think the danger may be that sometimes we find some nice tool and we say, oh, we can use the tool to eliminate jobs explicitly because jobs are expensive, right? Maybe mechanics or things that, you need people to do very complicated things. And you say, no, now we can do it with a robot. Big deal, right? I think that is the wrong way to go about it, but people could go about it. I think this is the danger.
Well, thank you very much. We're out of time. Let me ask you to thank the panelists for an outstanding panel.